put the mass of the pulley, right? This is the mass of the pulley. So what was the mass of the pulley? 1 kilogram. So now we're left with 2/5 A. So here is what we're left with now. We have 3 equations and 3 unknowns. We've got, let's write it here. Here's my 3 equations. 19.6 minus T1 equals 2A. T2 minus 9.8 equals 5A. And then the third equation is T1 minus T2 is 2/5 A. And the 3 unknowns are A, T1, and T2. Well, once you have 3 equations and 3 unknowns, you can solve this easily. Once you get the A, you can then answer any other question about the problem. We can add these 2 first equations. We end up 19.6 minus 9.8 is equal to 9.8 minus T1 plus T2, and then add these 2 right ones, that's 7A. And then now add that to the third equation. Then T1 minus T1 cancels. Negative T2 plus T2 cancels, as they usually do, because the tensions are internal forces. So when you add up all the equations, they should cancel because the acceleration should only depend on external forces. You see? So this cancels. So the only thing you're left with is 9.8 is 7 2/5. So 7.4. 7.4A. And that gives you the acceleration. One point Now, once you get the A of the blocks, the rest of the problem just falls through. It's like a building that just crumbles. You know, you take the cornerstone of the building out and, you know, everything just falls through. Because now if the problem asks me, what is the V final, what is the T? For example, let's say it wants to know what is the V final of the 2 kilogram block. You can use kinematics now. Right? Once I get the A, I can then answer what is the time, what is the V final. I have V initial is 0. And the distance that it's falling is 3 meters. Okay, so this is the method that we used is your typical force-torque method. Similar to the Newton's method that we were using in chapter 5. This includes Newton's law and the torque. Now let's do work energy. Work of friction plus work external is change in total energy. I'm using the chapter 8 version of the equation. So I'm going to put the total energy as the kinetic plus the potential. Okay? So here's what's going to happen. External works is 0 because there's no other object that's pushing this other than gravity. Friction work is along the, over here, it's going to be negative mu k n times the distance that this is going to travel, which is going to be the same as the distance this travels, so that's 3 meters. Negative mu k n d, right? And the normal force in this case is constant, so you don't need to integrate. Negative mu k n d, so that's the work done by friction. And then this is kinetic final plus potential final minus kinetic initial plus potential initial. Total energy final minus total energy initial. Okay? Now here you put whatever you need to. Let's see, negative mu k is 0.2. The normal force on the 5 kilogram is 49 newtons. The distance is 3. Kinetic final, now here's what you got to do. You got to think how many different kinds of kinetic energies are there at the end. Well, at the end, this guy is traveling. It has translational kinetic energy. 1/2 times 2 times V final squared. That's kinetic final. The 5 kilogram also has kinetic, translational kinetic energy. 1/2 times 5 times V final squared. Plus, the pulley has rotational kinetic energy, 1/2 I times omega squared. Now, the potential energy final, and then we'll put in what the I is and everything. Then we have potential energy U final. Well, U final, this guy hits the ground, so its potential energy is 0. This guy goes over there, so its potential energy doesn't change. So U final is 0. Kinetic energy initial is also 0. The U initial is going to be the 2 kilogram is at a height of 3 meters. So that's the initial potential energy stored. So 2 times 9.8 times 3. So now we've got, let's see here, negative 0.6 times 49 is equal to, this one's going to be 7 over 2, the final squared, plus half. Now you put in the moment of inertia as 2/5 mr squared, omega final squared, minus, this one is 6 times 9.8, 58.8, right? And then the 2 and the 2 cancels. And then the mass is 1 kilogram. And now here, look at this, R times omega. R times omega is V of the V tangential of the pulley, right? V tangential is R times omega, which is also equal to V of the blocks. Again, for the same reason that the A tangential of the pulley is equal to the A of the blocks. It's wrapped around the end, and the blocks are also tied to each other. So this becomes V squared. So you're left with negative 0.6 times 49 is equal to 7 over 2 V final squared, plus this is 1/5. The mass is 1 kilogram of the pulley. R squared omega squared is V squared minus 58.8. So this one goes over there. You combine this, solve for V final. You should get 7.92. Okay? Good job. Okay, so V final is 7.92. And now you could actually use that to find the acceleration in a backwards way. Okay? You could use kinematics. You could say V final squared is 2AD, and then take the 7.92, square it, 2A, and then 3, and then you can solve for A without having to do Newton's laws and torque. Now, I'm not saying that you should do that on the test, because if I put this on the test and I say find A, I expect you to do torques and forces to find A. Don't do energy, find V, then find A using kinematics. That's cheating. You're not allowed to, okay? If I ask for A, I want forces, torque. If I ask for V final, you could do it either method. If I ask for V final, you could do forces, torques, get the equation, get A, from A get V final, or you could do energy method to get V final. But if I ask for A, I want you to do, that means I want you to do forces and torques, okay? Because it would be kind of a weird way to get the V final from the V final, get back to the A, you know, cheating. Okay, so on